we will someone that couldn't join will join us. Okay, so welcome everyone. Hopefully most of the people joined. If not, I'll add them later, the one that couldn't join. Here, also. So we are now in the first presentation, slightly early from Monday when we actually start, because Bálint and Ben cannot join next week, so we didn't want you to wait for that. So again, welcome everyone. And this presentation was supposed to have like an introduction to the application, and I will let Ben and Bálint introduce it. So Ben and Bálint, just go ahead.
Yeah, sure. Okay. So hi. Right. So I'm Ben, and Bálint is not reacting. Okay.
Bálint,
I'm here. Yes.
Yeah. Okay. Right. Great. Okay. So okay. So we're going to talk a little bit about one of the challenges for the cluster, which is the DFTB plus code and some related tasks around this. So should we go to the next slide? Yeah. Okay. Right. Okay. Right. So well, we've both been working together now for a little bit over 20 years. So the history for this goes back to a research training network in Europe back around 2002 to 2005. And this was something called Renabel, which was about putting rare earth impurities into semiconductor materials to make optoelectronic devices. And so what they were trying to make was LEDs for different colored lighting. And as part of that, it turned out we had to write an entirely new code to do some simulation for this. And so at the time, both of us were based in Paderborn, which is marked on the little map on the left here, which is in middle Germany. And since then, we've both dispersed on a little bit. So my background is originally applying high performance computing for modeling, particularly of impurities and defects in crystals. So technique called density functional theory originally, and you know, I'm around long enough. I've been using things like Cray T3Ds, carrying on forward into these kinds of areas. And I'm generally interested in computational nanoscience. So this is problems in material science, condensed matter, some chemical physics, things like light and matter interactions. And so where I am these days now is in the city of Glasgow. So my university is the sort of middle child in that city. And we've been around for a while. And we're a technologically focused university. So we're the High Performance Computing Centre for the West of Scotland. So we have a tier 2 parallel platform here. But on the other side, we have at Edinburgh University, you've got the national supercomputing facilities for the UK. So we're in their shadow a bit on this one. And so I'll hand over to Bálint now, and he can say something.
Okay, thanks a lot, Ben.
Yep.
Ophir, could you go to the next slide, please? And so I'm Bálint Arad, and as Ben already pointed out, it kind of started together in Paderborn as a postdoc and dispersed from there. My background is actually quite similar to Ben's, so I'm also coming from defect physics during my PhD and making simulations with various density functional based codes on basically wide GaN semiconductors. And then after Paderborn, I moved to Bremen, which you see on the map. So if you know where Hamburg is by any chance, then Bremen is quite close. We are basically very close to the North Sea in Germany. And I'm not sure how much familiar you are with fairy tales by the Grimm's brother, but basically there's a famous fairy tale, the Bremen Town Musicians, about these 4 animals which you see on the picture, who at least tried to reach Bremen, and that's basically sort of also the became the logo of Bremen, or the marketing logo of Bremen. The original logo is the one with the key, and if you happen to drink Beck's beer, which is coming from Bremen, then you should have seen a similar key with pointing to the other direction. And if any of you is interested in Bundesliga by any chance, Werder Bremen still manages to be in the highest league in the Bundesliga at the moment. Okay, off your next slide, please. Then, as already said, my background is similar as Ben, so basically making atomistic quantum mechanical simulations. I'm working at the University of Bremen and in the Bremer Center for Computational Material Science. And basically our goal or target is to investigate functional materials, and we are investigating functional materials via modeling. And we have different groups on different modeling scales. And I am belonging basically to the group which is working on the atomistic quantum mechanical scale. And this is basically also my specialty. And of course, most of the time I'm also doing code development, so the DFTB plus code, which was already mentioned, and Ben and me being basically the main developers of the code. Next slide, please. Maybe I would like just to sketch you what this density functional type binding, which is the method which is implemented in DFTB plus is. And if you think about the method which you can use to simulate materials, then you can, following this figure here, you could sort of put them on the map where you have different time scales which you are able to reach with your simulation, and different length scales which you are able to reach with your simulations. And I mean, the axes are quite arbitrary, but there is a well-defined classes of methods. And in the lower left corner, you see basically the methods which are usually atomistic, very precise. So basically you can track the properties of the materials, or if you are talking about processes and reactions, you can track these reactions on the atomistic level using quantum mechanical methods. And if the problem with that is, of course, is that the resources it needs, and then you can go up and up to getting more coarser and coarser methods, like classical force fields, for example, where you have steel atoms as the smallest blocks, but basically the interaction between the atoms are not direct quantum mechanical anymore, but you are fitting some interaction which mimics quantum mechanics, but it does not include quantum mechanics directly. Nowadays, if you think about neural networks or different machine learning methods, that's exactly the same category, where you have to try to mimic material behavior, but you do not explicitly include quantum mechanics. And you can go even higher and higher in this hierarchy, like using finite element methods, if any of you knows, for example, just to simulate something of real size, which you can even hold in your hands. And the DFTB itself, the density functional based type binding method, is on the lower side in this QM region. That means that we are still including quantum mechanics explicitly into the equations which we are solving, but we are not the most accurate method. We have some approximations, and some parts I will talk about in a second are even fitted in order to speed up the process. But what distinguishes the DFTB is that basically you get a fast way of doing quantum mechanical implicit or explicit quantum mechanical simulations. Next slide, please. And basically just give you a rough idea, I just put a few figures of different problems or materials which have been investigated with DFTB. So basically there are not too many constraints what you can do. So whether you want to have something which is a solid, like investigating diamond nucleations, or some ceramics, or some clusters, or some biomolecules, which can be very interesting if you want to understand various biological processes on the atomistic level, or for example, light harvesting code. Those molecules can basically convert light into energy, into motion, and so on and so on. Or with the hybrid interface, several years ago, there were projects where people tried to understand the behavior of gluing materials between layers on an atomistic level and try to suggest improvements, how the gluing properties can be improved, and so on and so on. And even things like molecular electronics, where you are basically trying to replace conventional electronics with smaller devices, where basically your building blocks are small molecules between contacts. This is all possible to be simulated by the DFTB method. Next slide, please. I'm not sure what your background is, and therefore I will definitely not tell much about the physics and the equations behind the method, because I think that's not very, very important for the task, but nevertheless give you a rough idea what we are doing. I have 2 slides with very few equations. And if any of you ever learned quantum mechanics or heard about quantum mechanics, the famous Schrödinger equation, the Schrödinger, the guy with the cat, has to be solved. And that means that you have basically a system of many particles which contains all the electrons and all the nuclei in your system. And you try to solve an equation in order, actually an eigenvalue equation, in order to get the total energy. And as you can imagine, that problem is horrible, because the wave function which you have to calculate depends on the coordinates of all the particles. And if you know how many particles we have, for example, just in a gas, in a very, very small volume of gas, this is something you can never ever handle. And then there are various levels of approximations which are done. And I probably will not even go into the details, just telling you the buzzwords in case you want to look it up, or you ever heard about that, like the Born-Oppenheimer approximation, where basically we are using the fact that the nuclei are much slower than the electrons, and therefore basically we are putting away the degree of freedom for the nuclei, and we only concentrate on the electrons. Then the next big word is the density function theory. The Nobel Prize, I think around 2000 something, was given away for one of the founders of the density functional theory. So basically this is something where instead of concentrating on this wave function, which you see has still a lot of coordinates, a function with many, many arguments, you can basically concentrate on a single function, which is at the density of the electrons in the system. And there is a further approximation, which makes the so-called quantum approximation, where we are even assuming that these particles which are making up this density, they are not, they are basically independent in a certain way. And in that's the so-called density functional theory, DFT, and DFTB is just one step beyond, where we are basically assuming that we know a reference density, so basically what how this density looks like, and we only have to calculate the difference between this known reference density and a true density. You don't really have to know the details. The only thing you have maybe to know that we have, if you calculate the energy with that approximation, we have some terms, but maybe 3. We should concentrate in the 0-order term, the 1st-order term, and the 2nd-order term, and basically, to very, very simplify DFTB, the 0-order term is something we don't calculate, we just fit. And the 2nd-order and the 1st and the 2nd-order terms are terms which we are calculating explicitly. So we are doing solving quantum mechanical equations, but we are doing it in a strong approximation in order to make it fast. What does it mean, make it fast? If we compare with the methods one level below, the density functional theory method, we are roughly 2 or 3 orders of magnitude faster. So basically, that's what you have to imagine. Of course, for that, we have to make approximations. And in order to hide the effects of this approximation a bit, one part, the E0 part, which you see in the lowest equation as the first term, is not explicitly calculated, but basically approximated. So next slide, please, off here. Thanks. And just to come to the let's say the numerical part of the story, so all the approximations which we made and all the formalism which we are using are basically leading to an eigenvalue equation, or to be more precise, we have to solve the generalized eigenvalue problem. So basically matrix, that's the matrix H, the so-called Hamiltonian matrix, times the eigenvector C, is equal the eigenvalue epsilon times another matrix S times the eigenvector again. So if you ever had in math the eigenvalue problem, which I'm pretty sure you had, this is basically like the normal eigenvalue problem, with the difference that on the right-hand side you also have a matrix, which is just basically the so-called overlap matrix, but I think the details here are not so interesting for you. And basically, in order to create those matrices, that's for us in the DFTB method is very simple. So it's basically instantaneous. While if you are using more precise method, then you would have to make complicated integrations during the calculation in order to set up these matrices. But once you have these matrices, you have to solve basically the eigenvalue, the generalized eigenvalue problem. And the size of the matrices, you can basically think about that if you, let's say, 4 to 10 times the number of atoms. So each dimension of the matrix is 4 to 10 times the number of atoms in your system. So if you have 1,000 atoms, then you have to basically here diagonalize matrices of the size of, let's say, 4,000 by 4,000. It depends on technical details, which are not interesting here. These things are basically done within DFTB Plus, but we are not programming the algorithms ourselves. We are relying on external libraries, which are basically implementing efficient algorithms like LAPACK or MKL if it comes from Intel, and of course also parallel versions of that like ScalaPack, or they are specialized libraries which are providing even more efficient solvers like the so-called ALPA library, if you ever heard about that, which provides exactly methods for solving that problem, or in order to utilize GPUs, for example, the Magma library is able to provide the same functionality, but basically with GPU accelerations. And this is basically in the problems which you are going to solve, this is supposed to be the main bottleneck. On top of that, that's usually the biggest part of the calculation. We have another mathematical operation, a so-called rank K update. So once we have the eigenvalues that we are composing a so-called density matrix, which is this row here, which is basically a kind of summed up outer product of the eigenvectors. And those are basically the two leading terms in the mathematical calculations. One peculiarity of this method, actually almost all atomistic simulation methods, if you are talking about the quantum mechanic based one, is the so-called self-consistency. Basically, you can think about as an iteration to a fixed point, and where does it come from? I told you that we have to solve this generalized eigenvalue equation with the matrix H. But the problem is, in order to create this matrix H, we need something which we only obtain after we have solved the generalized eigenvalue problem. For us, those are the charges on the atoms. So think about that. You have an atomistic system, and you are solving in a very simplified way the Schrödinger equation, and then you get information about what was the charge transfer between the atom. You know, in the H2O molecule, you know that the oxygen is getting the electrons partial for electrons from the hydrogen. So oxygen is slightly negative, the hydrogen is slightly positive in a water molecule. And this information you need in order to create the Hamiltonian matrix. But in order to get this information, you have to solve the eigenvalue problem already. And that means it's a kind of chicken egg problem. And the solution is, which all these methods utilize, you are starting with an assumption over the charges or your electron density, depending which method you do. With that, you are building your Hamiltonian matrix. Then you are solving the eigenvalue equation. You get the eigenvectors. With that, you are calculating the new charges. With that, you build a new Hamiltonian. And you do it basically as long as you are not reaching convergence. And as I said, this is not just DFTB specific. This is very specific for most quantum mechanics-based atomistic methods. I just wanted to let you know, because you will see it when you run the code that there are some cycles done, and it tells you, okay, you know, we are in SCC cycle 1, 2, 3, 4, and so on and so on. So basically, we are just changing the charges, building a new Hamiltonian, solving it again, as long as it doesn't converge. Okay, I think that's more or less are the three numerically interesting parts in the DFTB algorithm. We may then proceed to have a look at that, what kind of input you have to provide to such an atomistic code. And Ophir, if you would go to the next slide, please. And thanks a lot. And then basically, in make a typical calculation for DFTB, there are certain things you have to provide. First of all, most important, it's an atomistic simulation, so you have to tell the program what kind of system you want to simulate. That means which kind of atoms it is composed of, and where are those atoms all sitting, on which position. And in a very simplified case, here is just you see a geometry which is a portion of a silicon carbide cluster, which is a wide gap semiconductor. And basically, just to show you, I am just listing how many atoms this system contains. In this case, it's a very small one with 64 atoms. And then I have the atom types in the first column and the coordinates in this format in angstrom, so in 10 to the minus 10 meters as x, y, z coordinates. And that's it. So basically, you tell the system what is the atomistic, what are the positions of the atom. This is the system which should be calculated. Then we have in DFTB, what gives partially the speed of DFTB, that we have this so-called tables which we store in advance in order to be able to very fast build up the Hamiltonian matrix, which we then have to diagonalize. And those integral tables, the details are really not interesting for the challenge, are stored in so-called parametrization files. These parametrization files have typically an ending of SKF, like Zeta Costa files, for historical reasons, and they basically contain the parameters which are necessary to calculate this atomic system, and those are pairwise parameters. So typically, if you have to calculate silicon carbide system, then you need a silicon-silicon, a carbon-carbon, and silicon-carbon interactions, but they are stored split in two files in order to be symmetric, silicon-carbon and carbon-silicon. That's the second input. And the first component of the input is basically, which you won't have to modify much, but basically you can set details for the calculation, right? There are different various methods, various approximations, various tolerance settings, and so on and so on. You can set up, and typically, depending on the problem, a physicist would play around with that because there is not one setting which fits all the material simulation calculations optimally. Many of the parameters the DFTB Plus can guess automatically, but there are some parameters which have to set by hand. But basically, this gives the physicist or the scientist who is making the simulation the possibility to choose not just the method and some details of the method, but also the precision which it gets at the end, the convergency, and so on and so on. And that's basically what is the main input. Next slide, please, Sophia. And then let's assume you made the calculation, then there are various different quantities which you can basically obtain from such atomistic quantum mechanical calculations. First of all, one of the most important quantities is the total energy of the system. So basically, what is of this atomistic system, what is the energy? Because based on that, you can compare different systems, different configurations of different systems with each other. What is energetically more favorable, less favorable, and so on and so on. If you think about electronic properties, like for example, for semiconductors, it's very, very important to know how looks the band structure of the system looks like, which is just basically the energy, the possible energies of the electrons in the system. And if you ever learned anything about semiconductor physics, then you might know that these energies are depending on the momentum of the electrons. And when you basically plot those spaghettis, which are connecting the energies or showing the energies independent of the momentum, then you have the so-called band structures. And this is the physicists and scientists can use in order to basically understand the electronic properties of the system, or even the optical properties of the system, and so on and so on. And one simplified quantity, which is not that spaghetti-like, but the wavy-like thingy with the mountains on the bottom, is a simplified picture of this band structure, more or less. So where you are not plotting each of the bands independent of the momentum of the so-called K index, but basically you're just counting how many states you have in a certain energy windows, and that's called density of states. And that's again is a very big help if you want to understand materials, the properties, the gap sizes, for example, the band gap. If you know the band gap and some other properties, you can also predict what kind of light it would absorb or emit, and so on and so on. There, or if you are talking about some semiconductor devices, which voltage you need, switch it on, switch it off, and so on, and so on and so on. And of course, there are also some additional properties you can derive, like changes in energy, forces, charges, and so on and so on. So there are many different quantities you can obtain, but I think at the moment that's not that interesting. Okay, then the next slide, please. Basically this simulation, this method, this among others, this DFTB method is implemented in the so-called DFTB plus code, and that's the one basically you will have to deal with. Just tell something about the project. It's a modern Fortran code. So modern Fortran means really we have even things from the Fortran 2018 standards. So it's whenever it makes sense, it's object-oriented. So as a modern language and project very often should be. We are talking about roughly 150,000 lines of code. Some of the tool chains around the code are written in Python, and this is an open source project under LGPL license. And of course, we would like to simulate big systems and long time scales, and therefore, of course, parallelization, it's also for us a very, very important issue. And we have different parallelization models in the code. We have thread-based shared parallelism, so OpenMP pragmas all over the code where it makes sense. We have message passing interface, so MPI routines, in order to also to achieve distributed process-based parallelization. And some part of the code via external libraries can also use GPU offloading, typically this the solving of this eigenvalue equation, which I have shown you, or this rank K update in order to create the density matrix. So basically, we are using all the possibilities to speed up the code or decrease the workload time one has to wait for a simulation. As for the community, it's of course because the code is just there. It's very difficult to judge, but based on the citations which we have, I would guess that we have roughly somewhere between 100 and 200 active research groups who are using really the FTP Plus code and making simulation with that and publishing scientific results with that. The project has roughly 10 regular developers who are really contributing regularly, and also of course, some casual developer. It's open source, it's on GitHub, so anyone who wishes to contribute is more than happy to join us or send a patch. Okay, and I think with that, I hand over to Ben, who will say a few more words about the actual assignment.
Sure, yeah, okay, so Afia, could you show the next slide, please? Okay, so a large part of what's embedded into this particular challenge is about the parallel performance of codes on multiple processor machines. So as Bálint mentioned, we have a few different parallel models that you can use inside of the existing code. So we can use some parallel libraries from ScalePack, or MKL also supports the same kind of libraries, but we can also use some higher performance potentially licenses like libraries like ELPA, and we can also use GPU acceleration too. But when it comes to performance of codes on multiple processors, the framework that most people talk about when we're analyzing the behavior for codes is to think about what's called the strong scaling behavior. So what that is increasing the number of processors that you are using to solve the problem, but keeping the problem fixed. There are related concepts where, as well as increasing the number of processors, you also increase the size of the problem. But typically people talk about the strong scaling as the most important thing to think about. And the equation that was proposed to describe this goes back to Amdahl, which looks at the speed up as you increase the number of processors. And so the equation on the right here is just the simple form for this. If your code performs a certain fraction of its operations in parallel, so you have a fractional amount that's that, 1 minus that is going to be the serial part of the code. And the serial part does not benefit from using more processors. It's only the parallel part which is going to accelerate. So looking at the equation here, we've got 1 minus p on the bottom of the equation, and so that's the serial part, which is going to be the constant. The parallel part divides by the number of processes n. So eventually what will happen, and you can see this in the graph on the left, is that the parallel part of your code will take essentially no time at all if you have enough processes, but you're left with the serial residual part, which is going to cost for this, because that's not spread out across this thing. And as you can see, the curves, when you plot this as a fraction of the parallel performance for this, will saturate at some point. And this is bad news in terms of getting high throughput, because if your code is not got a large parallel fraction, even using a few processes, as you can see for perhaps a code which is 50% parallel, gains very, very little from using additional processes. And from the point of view of running on a machine where other people want to use these, anything you're using once you get far down this curve whilst it's flattening out are wasting resources that other people can be using. So typically for highly parallel machines, you want problems that are being solved with parallel efficiencies of somewhat above 90% to be able to get large numbers of processes to efficiently calculate on these things. And so different algorithms and different sizes of problems can show quite different parallel fractions. So typically, if you have very, very small problems and very inefficient parallel algorithms, you can't gain anything from using parallel computing. But this is what you're going to be exploring in the challenge for this. So if you can go to the next slide, please, off here. Okay, right. So there are more details about this on the Confluence page for the DFTB challenge. And there's also the input files and some guidance about libraries and compiling for the clusters on this one. So if you've not looked at this already, have a look at the Confluence page for more details. But the idea here is to use DFTB Plus on 4 nodes of the Iris cluster with a set of input, which is set up for this silicon carbide system Bálint was talking about a little bit earlier on. So this is a perfect crystal, but is repeated out to infinity with copies of the same unit cell for the crystal. And so the idea here is to run this and have a look at the output for this and submit your output onto the Teams folder, and also have a look at your performance for this thing. So time out how efficiently the thing is going to work. So look at how fast you can get your results through, ideally with some reasonable speed up instead of wasting resources, and put your information at build scripts and run scripts again into the Teams folder for this one. Then a little bit more computer science is to examine the behavior of the code using a profiler to have a look at the main pieces of the operation for this. Bálint has given you a few hints about the kinds of areas you're likely to see costing most of the computational time, but again, show your work in the Teams presentation at the end of this. So this is going to be something you're going to probably want to do graphically, and have a look at your execution time with different numbers of CPUs and nodes, because on the cluster, you're able to use up to 4 nodes. Obviously, each one of those has got multiple CPU cores. So have a look at this, analyze the strong scaling of your input. Try and figure out what fraction of your calculation is actually working in parallel. And we've given some pointers towards using a couple of different methods out of the libraries that we use to solve this generalized eigenvalue problem. So scalar pack QR is one approach, and the ELPA solver is another one, and they will potentially give you quite different parallel fractions and behaviors on this thing, but this is something you're going to investigate. And so once you've done that, present these results graphically. Now, the Amdahl's law is an idealized version of this kind of behavior. You can have situations where Amdahl's law doesn't actually describe behavior, because as a theory, it was derived without thinking about things like the performance of the parallel network in the system. So you might get some surprises if you try this. Okay, then once you've done all of this, visualize what you're doing and produce a short video or a set of images and put these into the Teams presentation. And that's the main things that this task is going to be asking about. But as I say, check the Confluence site for the actual inputs, some hints about getting the code up and running, and more detail about these tasks. Okay, I think that's everything we're going to say today. do we have maybe some questions?
Yes, thank you, Ben and Bálint. Anyone, if you have any questions, please maybe raise your hand or start talking. I will say that the wiki pages, the conference pages, I sent them in the Slack. I will resend them again, and the links to that are on the website. So if you are on the competition website, you should be aware of that. I'm sending links to that all the time, where the agenda is. So if you go to benchmarking, for each application, you will see a link to the wiki pages that we have. Okay, anyone, any questions? Everyone, everything is understood, easy?
Well, we hope so.
You have any? Okay. Do we have any questions? I don't see anyone who wants to talk, which is fine.
So,
I mean, yeah, no one has really started, so I think it's questions may come as we go, and please join our Slack. It's meant for you. I want to say that from previous years, don't stuck on things. If you are stuck, you are, you cannot. You scratch your head. You don't hit your head on the wall. Give us a question in your Teams folder, or if it's something generic, you can use the main channel or in the Teams channel as you feel, and we'll try to help you. And the idea here is that you will learn, you will experience working in benchmarking application that are used in the industry. And hey, I see one question from Niels. Yeah, go ahead, Niels.
I have a question. Is there a possibility of changing any input files regarding tuning? Like, is there any parameter that we are allowed to change that has an impact on the performance or on the type of simulation that might enhance the performance?
Okay. Well, probably the main thing to check is changing the parameters about which solvers you're going to use. So we have some example settings for this kind of thing. So the way that we provide solvers, I wonder if it's worth going back to the picture with the library dependencies. But we have several different provided solver choices about these kinds of things. There are some slightly more special purpose ones. So some of the solvers show very high parallel scalability, but only for very specific types of problem. The ones that we're suggesting that you check between are what's called a QR solver, which is one of the most general purpose and stable ways to solve the eigenvalue problem in this space. But ELPA also then has a couple of different settings as its method, and the internal difference between these is somewhat different. So internally, the algorithms behind these methods typically proceed by starting with a large dense matrix. It then makes transformations on that matrix to go to a special form where the elements are only along the three lines of the diagonal of the matrix. And both ScalarPack and ELPA do this with different strategies. Then once you have transformed to what's called a tridiagonal matrix, you then find the eigenvalues and eigenvectors of that special form. And again, there are some difference in the algorithms that the QR ScalarPack and the ELPA type 1 and type 2 are using to actually resolve that. Once you've done all that, you run these transformations backwards again to make the resulting eigenvectors compatible with the original matrix structure. And so this kind of operation is going to have some impact on this. There are some other settings in the input file which would change the runtime. So, for example, Bálint mentioned about scientists sometimes changing settings about, for example, the fixed point iterations. The problem with changing those kinds of settings is if you adjust these things, you can make the quality of the resulting solution converge very rapidly and stop iterating, but the quality of it can be lower. So that kind of setting is possible to change, but you're going to potentially get the wrong answers if you do this. So we're not particularly suggesting you experiment with that part of it. So we put some safe settings in for converging this. Did I miss anything, Bálint?
No, I think exactly this is what I would have to say. So don't change the physics settings or the accuracy settings. You might play around with the algorithms which are doing the real workload and test whichever are working better. Yes, exactly.
So the only changes allowed that don't change the actual output of the simulation.
Sorry, I had some problems to understand you acoustically.
Yeah, I didn't hear as well.
So there are no changes allowed to be made that change the kind of resolution or output quality also.
Yes, so the output quality should not change.
Okay, so no matter what we change in the algorithm, okay, we'll always have the same output. For sure, at least if we're doing everything correctly. Because in the last test, there was like the ability to change stuff that resulted in different outputs. Okay, I think I'm doing the way to hear.
So
Okay, maybe type into the chat might be a little bit easier, because the audio is unfortunately not working very well. So mentioning the chat, there is also a question in the chat there, I see. So Ophir, this is maybe more for you.
Yeah, Niels, we couldn't hear you well. I'm trying to answer the question about the on-site part. In general, for the on-site, we'll have the same applications, but the actual tasks will be smaller because we don't have a lot of time on the on-site. So we'll, we will publish that closer to the on-site part competition, which is in June. So we still have time for that. But if you are on the on-site teams, you can try the virtual if you want to get familiar with the application. And actually, it will be good for you. So get familiar with the application, and then we will discuss internally DFTB Plus and all the other applications, and create the task for the on-site part. Okay. Niels, can you write your question? And we couldn't hear you well, at least I. Anyone else wants to ask anything, by the way?
Okay, we have another question in the chat about GPU acceleration.
Yeah.
So, yeah, okay. So the actual core code for DFTB itself, when it's setting up the equations to be solved, at the moment does not really rely on GPU acceleration at all. But some of the linear algebra solvers that we can interface to will be able to use GPU acceleration. So Bálint mentioned about Magma, which is something we've not talked about too much in terms of the challenge, but that one is specifically for solving the eigenvalue problem and this rank K update on GPU systems, and the code can be compiled to use that. Alternatively, ELPA, if you have one of the more recent versions of ELPA, you can compile with GPU acceleration. So the compilation is a little bit more complicated because you need to build ELPA independently with GPU acceleration in place. But that would then make use of any GPUs that are on the system. Ophir, I don't know if you can comment whether there is any GPU.
I'll comment that we didn't aim for GPU for this task, so CPU only. If you wish to experience with GPU, try it. You can, but you have to do it on the Romeo cluster, on the other cluster. It's not part of the task, but again, and then we didn't test it when we didn't prepare for that. So it's up to you. I don't know if we give credit on that or not. Probably not. But if you want to, for yourself, experience with that, you can. For the task, we ask only to do it on the CPU cluster for this application. How's that? How about that? Okay.
And just Niels, just to I see your question in the chat. Yes, you should get with the numerical tolerances basically the same results. Yes, so if you get something completely different which doesn't look like the previous one, then something is wrong.
Yeah.
Right. So basically we want to get out the same physics, basically the same numerical results, a part of numerical inaccuracies, but using various different methods. And please also don't try to speed up the method by trying to compile everything with the most aggressive possible mathematical optimization, because that's in very many algorithms doesn't work, right? So I mean, you may try it, but that could be tricky, because many algorithms are not very well working with aggressive compiler optimization.
Yeah. So a lot of compilers, if you really push it, start to break IEEE compliance for mathematical operations. So as a result, you know, what comes back out can be quite different.
Good point. Any other questions? Okay, so what I suggest is, anyone has any other questions, again, please use the Slack. It's our lobby room, channel room. You have a team. All the developers and most of the committee members are already in your team channels, so you can use that. And I would like to invite you next week on Monday, 9 a.m. Pacific time. It's a GMT +7 because we are in summertime, so I'm not sure wherever you are. If you're already in summertime, make the calculations when it is, but it's 9 a.m. in the Pacific time. We will have the opening ceremony, and just after that, at 10 a.m. Pacific time, we will have the introduction to the AI task. And then on Tuesday, we'll have 3 more team meetings, Zoom meeting for that. So just stay tuned. It's a little bit packed in the first days because I want you all to get it quickly as possible. So and then the access to the clusters, at least for Iris, you will get on Monday. And Romeo, you should either get it this weekend or by Monday. So by Monday, you should all get access to the clusters. On Romeo, you will get email. The team captains will get emails from the IT managers of the Romeo cluster. Okay, on the Iris cluster, you will get email from or on the team chat with the credentials and how to access the Iris cluster. Okay. I see another question from Henry. It's fine to run normally first to determine the correct answer, then start cutting down iterations, whatever, to make it slightly faster.
You could cut down iterations, but then you won't get the same answer anymore, right? So there's always a trick to get more approximate or basically converge all the results less and less, but then that won't be the same. And it's I think in this kind of competition, it's a little bit difficult to argue, because then you would have to start to argue with physics to say, okay, for this physical quantity, this precision is still enough because. So I don't think that's something. I mean, if you can argue about that, that might be an option. But usually that's the more physics than computer science.
Yeah, I would say that normally we ask not to change the physics, and the reason is that we want to compare everyone with the same physics, same number of iterations, same algorithm, same, you know, on the physics, on the compilation, on the MPI, on the, you know, how to run it, how to spawn it on the cluster, how to use the nodes, storage, all that you can change. So things that are not related to the actual problem, you can change how to run it.
Okay, so we have another question in that direction in the chat again. So it is extremely difficult to get bit level correctness from almost any algorithm. So in this general field, there was a science paper about 15 years ago where 20 different codes all compared calculating the same system. And the very best ones agreed to about 6 decimal place in quantities like energy in the right systems. So this is kind of the tolerances that this field works to, that for things like total energies, you have however many significant figures, but typically you want to work to about maybe milli is a little bit too loose, but perhaps tens of micro in this energy unit system. Likewise, quantities like charges or structural things. For structural accuracy, people typically work so that the distance between atoms are accurate to something less than 1%. And for charges, it's typically maybe 1 part in a few hundred or so, something in that kind of range. So some of it depends on what you're going to use these quantities for as to how accurate you need to make them. Because if you put things into calculations where you're taking differences between things, you have to have much higher precision because you want to deal with error cancellation on large digits, so that the residual parts of it are just going to be accurate enough to give you something sensible. But if you want absolute quantities, then people work to certain tolerances. But a lot of it depends on the error bar for the experimental quantity that you're trying to understand, for example.
But just a very quick comment on that. I mean, you can see it yourself. If you're using different compilers and otherwise you use the same libraries, just with compiled with different compilers, you will see that already there the results are not bit equivalent, right? So even there you have differences already of the order of 10 to the minus 12. Roughly same algorithm, same library, but just different compilers and therefore different optimization path with or mechanism with the compiler applies.
Okay, so we are very close to the end of the hour. I think it's a good point to close it. Again, if you have any more questions, don't stop. Ask us. If you're not sure, ask us. We'll try to help wherever we can. I mean, we hope you grow your mind here, experience, use the cluster resources that we are given, and we'll give you to experience with that. And hopefully, again, enjoy. And might see you in the future working on those applications or one of those applications if you're getting interested in this field. Okay, so again, thank you, Ben and Bálint, for a great presentation. And everyone, see you on Monday, 9 a.m. Pacific, for the opening ceremony. We'll introduce in general all the tasks and everything. Okay.
Okay. Thank you, everyone, and have a nice weekend.
Bye, everyone.
See you on Monday.
Take care. Ciao.
Bye.